for gapless phases and try and apply it to systems in 2D with an emergent Fermi surface. And then when I finish that, then I want to touch on numerically detecting topological order to sort of complement Lukáš and Youngbuck's talks. So what we discussed last time was what happens if you use infinite DMRG, so DMRG in the thermodynamic limit, on critical Hamiltonians. So you're given some lattice Hamiltonian for a CFT. You just run DMRG using a bond dimension or accuracy chi, and you get out this matrix product state representation of the ground state. And what I tried to argue last time was that if you look at this matrix product state, even though the exact ground state would be gapless and have algebraic correlations, the matrix product state you get out always has a correlation length, which I called the finite entanglement correlation length. And it scales actually as a universal power law with exponent kappa with the bond dimension chi of the matrix product state. And Frank Pullman et al. Had this really cool argument that the exponent kappa depends only on the central charge C. The derivation of this kappa won't actually be too important. The conceptually important thing is that the DMRG just introduces this new length scale. So now I want to explain how you would extract some other things. Like if you have a conformal field theory, you don't just want to know its central charge. You also want to know things like the scaling dimension of operators. So how would you compute that? So the idea is, suppose I had some operator I'll call O sub I. You could think of this, for instance, as being the magnetization operator in the transverse field Ising model. And suppose I want to calculate what the scaling dimension of it is. So I'll write that as delta. So we know in the exact ground state, if this has scaling dimension delta I, and I look, for instance, at a 2-point function, the meaning of it being a scaling operator is that this would go as a power law as x to the 2 delta I. So if I had an exact ground state, it would be very easy to compute delta. You just compute the 2-point function. The difficulty is I'm not going to be given the exact ground state. I'm going to be given this matrix product state approximation to it. So the useful idea of this CFE is you do the following. So let me define CI, the correlation functions at distant x, and finite entanglement scale C is just defined to be you take the output at that accuracy and you measure the 2-point function. So the idea is because I'm at a critical point, all three objects here, C, the distance, and the finite entanglement correlation length, all have a fixed particular dimension. So these have dimensions of length, and C has dimensions of 2 delta set by the dimensions of these two operators, which are the dimensions we're trying to extract here. So as we can usually do in any scaling theory, this function here obeys a particular scaling transformation, which is I know that this is equal to the usual scale transformation, negative 2 delta CI. So what I've done is I took this function here and I did a scale transformation by C of f of e. So 3 things are going to happen. The object as a whole has scaling dimension 2 delta because these were scaling operators. So that's why this factor came out here. And then you replace the argument here by c x over c, and then this has been scaled to 1. So the point is I've been able, so you originally would repeat the DMRG numerics many times for different chi's, and you get a bunch of different values for this finite entanglement correlation length. You take all your data sets, and then you just replot them as a function of the distance x over the correlation length of the matrix product state. And what you should find is if you plot all of these data sets, if you pick delta correct, all of them will collapse onto the same curve, and you know you've extracted delta. Whereas if you guess the wrong delta, then they'll be shifted relative to each other. So then just by twiddling around with delta here and looking for collapse, just like you would with finite size scaling, you can extract the scaling, the scaling exponent.
And how many different values of chi do you try?
Well, just like usual finite size scaling, in order to see the power law, you'd try and get as many decades of correlation length as you could. So you might just start at bond dimension 20 and go as high up as you're willing to spend the time on. So maybe you'd do 10 different values of bond dimension between.
How does it compare between the Emergent and gas system?
It's faster usually. At the same bond dimension, this is faster than doing finite DMRG. Because finite DMRG, what you'd be doing is you'd have to simultaneously grow the length of the system. That's the size. But then as you do larger systems, you also tend to have to use larger bond dimensions. And the cost goes up linearly in the length and as a power law in the bond dimension. When you use IDMRG, you never grow the length of the system because kind of for free, it's already in the thermodynamic limit. So all you're doing is increasing the bond dimension. So I don't want to guarantee it's faster, but a lot of the times it's faster to do this than the finite size version. I think if you're actually just trying to calculate properties of 1D CFTs, either are going to work because it's just not that hard. But the application I want to talk about is doing this for systems which are actually two-dimensional, and you're studying on a cylinder, and then it can be so hard that like eking out this extra efficiency by taking the thermodynamic limit can be crucial.
So technically, so in IDMRG, you continue. What is the convergence? How convergence is achieved?
Like convergence in, say, the energy density, for instance? Is that what you're asking?
I mean, like if you want to keep the chi constant, then, I mean, is there a criteria of how long you go with the IDMRG? Because then it depends on that. If you don't converge exactly on all of them, I mean, I assume this is exact. And does like, if you go all the way to like complete convergence.
Well, sorry, do you mean converging do you mean converging the behavior in the bond dimension?
No, I mean keeping the bond dimension constant. You want to like continue IDMRG until convergence. You have to stop, like for example, you go all the way until energy is like 10 to minus 8, 10 to energy, or maybe you can't achieve that. So doesn't that enter that equation somehow?
Yeah, okay, so if you fix the particular bond dimension, of course you can never actually correctly get the ground state because the ground state would require infinite bond dimension. But I think you're asking how long do you have to run the DMRG such that you get the best state at that bond dimension?
Yeah, that's exactly.
Yeah, with the best algorithms, like there's a recent one from the Verstrata group. For any fixed C, it will still actually converge exponentially quickly. Though you will find that as you increase the bond dimension and this correlation length becomes larger, it does take more steps to converge.
And my point is, at each step, you have to find the best state at each class, right? At a class of 20. Yeah. So this equation is for exact ground state at that class of chi equals something.
Yeah, maybe I wouldn't call it ground state, but the variationally optimal.
Yeah, the variationally optimal.
Yeah.
So, well, you don't know that we have found that by DMRG, by using IDMRG, right?
I mean, in practice, the IDMRG always seems to find the near variationally optimal. I mean, technically, the two-site DMRG isn't variationally optimal, whereas the Verstrata group has a version which will find the variationally optimal. But somehow it seems that as long as you do the same thing, like use the same algorithm at each chi, the details of the algorithm, you'll find a slightly different state, but by doing the same thing at each chi, you still get the same scaling collapse. That's what seems to happen. Yeah, and I want to show you some data from Frank's paper. Here what they're doing is calculating, so one way you could try and get the central charge is by looking at this exponent. In practice, just because of the way this behaves, it's kind of flat as a function of c, and it's not a very easy way to extract the central charge. The easier way to do it actually is to measure the entanglement entropy for a cut of the system, so it's infinitely long, and you just cut it into A and B. and you just measure what was the entanglement entropy as you increase the accuracy of the DMRG. And this should take the form C/6 log C finite entanglement plus some constant. So you repeat the DMRG, you measure the entanglement, and you measure the correlation length at each bond dimension, and then you plot it on a log linear plot, and the prefactor here is going to tell you the central charge. So let's see, how do I turn on the screen? Though equivalently, I could write this as C kappa. Oh, this isn't plugged in. Oh, no, it is. Okay.
It is, but...
Oh, no, I just want the... Can I just do it on the side? Yeah. Okay, so what I'm going to show you is the paper where they derive this kappa, how good this collapse tends to be. So what they're plotting is the entanglement as a function of the bond dimension in the DMRG for a couple different conformal field theories.
Malfunction of the system here. It's not on. If you want, we can just put it on the projector real fast, because that'll work.
Okay.
But the TVs are not.
That's too bad. This won't be a very efficient way to... Right, so here they've taken a couple different conformal field theories. One has central charge 1/2, that's the transverse field Ising model. And they have some C equals 1, 2, et cetera. And they're plotting exactly what I said here, the entanglement versus the bond dimension used in the DMRG. And then using this particular value of kappa, the dark lines are what they expect. And you see this beautiful log linear growth in entanglement with chi. Okay, how do I... Can we try a little harder on the TVs? Because there's another... Yeah. Okay, so I want to discuss an application which is trying to detect emergent Fermi surfaces in 2D systems. So the idea of emergent Fermi surfaces, or non-Fermi liquids in general, there's a couple scenarios where this comes up. So one are for instance, the gapless spin liquids that we heard about earlier. So this could be, for instance, a spin-on Fermi surface in 2D. Another case occurs in the quantum Hall effect, is what's called the composite Fermi liquid, so CFL. This occurs at half filling of a lambda level. And what's common here is you have some fermionic object which forms a Fermi sea, but that object is not actually the microscopic electrons. So a question you could ask is, if you're given a microscopic Hamiltonian, how could you numerically detect that there's this emergent Fermi surface of objects which aren't fermions? So I want to discuss how you can use this finite entanglement scaling idea to attack the problem with infinite DMRG. So the approach we'll take is, because DMRG is a 1D method, you need to take your 2D Hamiltonian and study it in some 1D geometry. So the really nice one to use is this cylinder geometry. But by doing IDMRG, the cylinder is actually completely infinite in one direction, but then has some particular circumference L in the other direction. Okay, so you could take your lattice Hamiltonian and just periodize the boundary conditions. And then formally, this now looks like a 1D system. So in practice, to do the IDMRG, you have to choose the so-called snake. So like, let's say I had a square lattice that looked like this. where this side up here is identified with this side down here. In order to map it to a 1D model, you just order the sites like this. And now formally it becomes just a one-dimensional chain, but with kind of funky interactions because this site has to talk with this site, et cetera. But still, you can just put this Hamiltonian into the IDMRG and then find the ground state. So now the question I want to ask is, given that you've run the DMRG, how would you detect one of these emergent Fermi surfaces of something which is not a fermion? So naively, what you might think to do is, for instance, you could find the ground state, chi, and then just, let's say you started out with an electron system, so like in the quantum Hall effect. You could measure what is the probability to occupy one of the electron states at momentum k. So this is the momentum distribution function. Now, if this was forming a regular Fermi liquid, if I was to plot this occupation here, it's a function of momentum, the whole meaning of a Fermi surface is you'd find that n of k is 1 within some circle, because you filled it, and 0 outside, and then by marking out the discontinuity in k here, you would have measured the Fermi surface. But for systems like this isn't going to work because it's not the electrons actually forming the Fermi surface. So if you were to plot this electron distribution function, it would just look completely incoherent. It would be some smooth distribution. So the idea instead, and there's a couple different ways to do it, is to think about what the entanglement would look like if a Fermi surface was forming. So to warm up, I actually want to start by focusing on the case where it was actually the fermions forming a Fermi surface. And let's actually just think about what completely free fermions would do. So a nice way to think about it is if I have the cylinder like this and I have a coordinate system x going along the cylinder and y going around, the original electron operator is psi of xy. What I can decide to do is Fourier transform and keep it in real space along the x direction, but go to momentum space along the y direction. And because I'm on a cylinder here, the momenta ky become quantized. If I have periodic boundary conditions, then I would get that these are inside 2 pi for L times n. Now you could actually, one trick you can play is fiddling with this a bit, because if you put flux through the cylinder, you can twist the boundary conditions and change what momentum are actually allowed to show up here. So what I then get is, if I look at my Brillouin zone, ky, kx, and suppose I think there's a Fermi surface forming here, because of this quantization condition, what you're effectively do is restricting the Fermi surface onto a set of discrete momentum like this. So these are the modes here separated by 2 pi over L. Each of these I kind of think of as being a mode or a wire, which is one of the allowed ky's. In the limit where it's completely free, the different momentum don't even talk to each other at all. So each of these momentum sectors itself just forms a one-dimensional Fermi surface whose kf depends on which momentum ky you're looking at. So in this limit, we can actually treat the system as if it's a collection of one-dimensional gapless states which descend from the actual 2D one. So we can ask questions like, for instance, if there was a Fermi surface, what do you expect, if you view it as a 1D system on a cylinder, what do you expect the central charge to be? So in the case where these are fermions, each of these modes here, it's known that if you just have a free fermion in one dimension, it carries central charge 1. If these were Majoranas, it would have central charge 1/2. But so in this case, what you'd get is that the central charge, C, would be equal to 1 times the number of modes. And the number of modes here is going to be the width of the Fermi surface. It's kf, or at least approximately equal to kf divided by the distance between the wires, or sorry, 2kf divided by the distance between the wires equals L kf over pi. So the prediction is pretty simple. It says that if we were to measure the central charge for a sequence of cylinders with progressively larger circumference, I should see the central charge going up linearly in circumference. There's another name for this, which is the Whittam law, the L log L growth of entanglement. So let's plot what this would look like. If I do L here. So first of all, can anyone say, will all the central charges show up? Will I see central charge 2? As I increase the circumference of the cylinder. So let's draw it. Suppose I have a Fermi surface like this. If I start out with a really, let me do a small circumference cylinder, then it would get cut by one wire at the center. But then the other wires are going to miss it. So in this case, I'll only see central charge 1. Now, as I make the circumference of the cylinder larger, the spacing between the modes comes in. And what you'll see is so long as you have reflection symmetry, this wire and this wire are going to start cutting through the Fermi surface at the same time. So what you're always going to see actually is once you get to a larger circumference cylinder, the central charge is going to jump up by 2. So you can see here that the central charge is always going to be 1. So if I plot C versus the circumference, it will be 1 for a while, and then it will jump up to 3, and then jump up to 5, sort of like that. But overall, it would have linear slope and 0 intercept. So that's kind of a defining feature of something which would be a regular Fermi liquid. So are the TVs working?
Getting there, but not yet. Supposed to be on projector.
Depends what the estimated time of, or we don't really know. Yeah, okay, we could switch them.
Put the screen like halfway down.
Try that.
So that we can see the border.
Sure.
Is there markers then, so I can use the sideboards? Okay. Well, that's pretty good. Okay, so I wanted to show you some data of actually using this approach. So the system we're looking at here is it's a quantum Hall problem. So you have a lambda level, which is exactly half filled. And it's long been thought and basically known that if you half fill the lowest lambda level, it actually forms one of these emergent Fermi surfaces. So what you can do is we then run infinite DMRG by putting the problem on a cylinder and then do this finite entanglement scaling. So the left plot here, so there's kind of a lot of data to show. If I take one particular plot marker, that's the circumference of the cylinder. And we repeat the DMRG and we get various correlation lengths. Those correlation lengths, the finite entanglement correlation length, is the x-axis here. And then we plot the growth of the entanglement entropy as we go along. So what we see by putting on a log linear plot is all the data collapses onto a straight line. And if we assume that it has integer central charge, the slope of that line are the possible dashed lines here. So the first group at the bottom are circumferences where what you find is that the central charge is 3. And then you find that there's a critical circumference of the cylinder where it switches from brown to green, where the central charge jumps up by an integer to, in this case, you happen to see 4, and then even wider it goes to 5 and then 7. So what we've now done is been able to measure what is the central charge of the system as a function of the circumference of the cylinder. And you find that it indeed fits onto a line. And now I want to discuss why the details of this actually show that this is a non-Fermi liquid rather than a Fermi liquid. So we saw for a regular Fermi liquid where it's electrons, there's two things we expect to see. One is that the central charge you're going to measure is always going to be odd, just because the wires come in pairs. And the other thing is that the central charge is going to be linearly proportional to the circumference of the cylinder without any intercept. So when I plot C versus L, it should have an intercept of 0. If you look at this data, we see that it's already violated on the first count. The central charges that are showing up is 3, 4, 5. If we had done more data, you'd see 6 and 7. So we're actually seeing both odd and even central charge. The other thing you would find is if you fit the curve that I've actually fit it with is that the central charge is equal to L over pi minus what I'll call gamma, where gamma e is equal to 1. So it's still linear in L, but it has this weird offset, which has less central charge than you'd expect. So both of these are actually really nice evidence for the fact that it's a non-Fermi liquid. And the sort of analysis I'm going to explain you could apply to spin systems or any time you think you have one of these emergent Fermi surfaces. So what's happening in these cases with an emergent non-Fermi liquid is that you have some object which is a fermion, which I'll call psi. So this could be a composite fermion, or it could be a gapless spinon. But what's interesting about them is if you look at their effective action, it will be something like a Dirac equation, but it actually couples to an emergent gauge field. So this is exactly, for instance, like the U1 emergent gauge field that we heard about earlier today. And the fact that the fermions forming the Fermi surface coupled to the emergent gauge field can actually explain both of these effects. So the reason is, when I first drew these wires, I said that the momentum of the fermions, ky, was equal to 2 pi over L times an integer. But when I wrote this, I was implicitly assuming that the objects I was Fourier transforming had periodic boundary conditions. But you could ask, what if, for instance, the objects you were Fourier transforming had anti-periodic boundary conditions? Then you would put a plus 1/2 here. You'd get half integer momenta showing up. Now, if it's physical electrons you're discussing, you choose the boundary conditions just when you define the Hamiltonian. But in these cases where the fermions are emergent and they couple to this emergent gauge field, the boundary condition that these fermions see is not actually chosen by you, it's chosen by the gauge field. Because if you put the system on a cylinder like this, the emergent gauge field can put whatever sort of magnetic flux it wants through the cylinder, I'll call it phi sub a, and it's a dynamical degree of freedom, so it can just choose what flux to put through the cylinder depending on various energetic considerations. So that means even if the Hamiltonian microscopically has periodic boundary conditions, the fermions could see either anti-periodic or periodic boundary conditions. So what's going to happen is as you change the size of the cylinder, let me do this same sequence again. You might find that for small circumference cylinders, the gauge field is such that it sees periodic boundary conditions. But then when you go to slightly larger cylinders, the gauge field decides on its own to thread pi flux through the system. And now the objects now see anti-periodic boundary conditions, and you can actually put 4 wires through rather than 3 or 5. And then you go to larger and so on. So this actually explains why here we're able to see 3, 4, 5. Each time it switches, the emergent gauge field threads flux through the cylinder.
So what was that name? Coulomb?
This Hamiltonian, yeah, it was Coulomb Hamiltonian.
Why does it have to be Dirac Fermion? Can it be just
yeah, sorry, I should
the
have.
gauge field?
It doesn't necessarily have to be Dirac. I mean, it's actually important here that I have a Fermi surface. So if it was, in this case, I've written the Dirac equation, but it needs to be at finite chemical potential. So it's like it's a Dirac cone, which is filled like this. You need to be at finite density such that there's actually a Fermi surface. Otherwise, you wouldn't expect the central charge to increase with circumference. Yeah, no, you're absolutely right. I wrote this, but I could have also just put just a massive p squared over 2m type of, yeah.
I guess it's the title of the paper.
Yeah, it's because it's the
Make it
title of the
sound
paper
like-
I said Dirac. Yeah.
Did your position change since the paper?
No.
From-
So,
But the title of the paper says it's the case for Dirac composite fermion. But now you seem to say that it can be either way.
well, I'm saying at least this effect of you could get a Fermi surface either by taking Dirac and doping away from the Dirac point, or by having regular p squared over 2m. This argument here doesn't really care about whether the dispersion is linear or quadratic. It's really probing the fact that it's coupled to a gauge field.
So then in that case, the gauge case for Dirac was something else.
Yeah, that was some other properties. This here is evidence that it's a Fermi surface coupled to a gauge field. The Dirac is not probed by this. I think there's another question. Michael? Yeah, so the other thing you can measure here, I don't have it up, is so I've drawn the wires like this, and I've drawn a circular Fermi surface, for instance. But just measuring the central charge doesn't tell you that. It's only telling you the number of wires, right? So you could definitely ask, is there other evidence you can get to say that the Fermi surface is actually a circle or something like that with wires configured like this? So I wasn't going to talk about this so much, but what you can look at is, suppose you pick some operator like the density, I'll call it rho, and you can measure the structure factor, like rho of q, rho of like this. And what you can look for is peaks or non-analytic kinks in the structure factor. And what you would expect these arise from is if you choose a particular configuration of the Fermi surface, say like this, the low energy excitations here involve scattering one of the fermions from this part of the Fermi surface to this part of the Fermi surface. Sorry, I draw this here. With some particular momentum. And you expect for any low energy process like this with momentum transfer q star, it will show up as a kink in the structure factor at that momentum. So what you can do is measure the structure factor and plot out the kinks, and you'll find that they correspond to the various momentum transfers allowed by a Fermi surface configuration that looks like this or that. So that's kind of the consistency check on it. And that actually tells you, for instance, whether the Fermi surface is a circle or whether it's deformed into an ellipse or something like that.
It also gives you directly the right wave vectors for the four.
Yeah. Yeah, that's correct. Yeah, exactly. Yeah, so in this paper, you'll actually see a plot of doing that analysis, which is kind of nice.
But this behavioral switching sectors, this is the finite size effect, but basically.
Yeah, so there's,
You're using the finite size effect.
yeah, you're using the finite size effect, yeah. I mean, basically what it tends to do is the gauge field prefers to shift itself such that you can kind of neatly fit in the right amount of wires. So, yeah, and that's all like 1 over L kind of finite size effect.
Finite size of 1D, quasi 1D.
Well, yeah, it's finite size from the direction which has been made compact. Yeah. Okay, so this has explained how you're able to see both odd and even central charge with this dynamical boundary condition. I also want to say where this factor gamma comes from. It's a little bit like, I don't want to say topological entanglement entropy here. It's a shift in the coefficient of the central charge. So that also comes from the gauge field. So basically the idea is if you have an emergent gauge theory, it's possible to create a pair of objects. So for instance, I can make one of these composite fermions.
Question.
But, yeah.
So you just claim that the flux happens to be changing depending like that the size. But
Yeah.
isn't that kind of fixed by theory that you wrote down the Dirac fermion by the density of the fermion itself in the flux?
Well, yeah, so there's two types of flux. There's the flux, so if I have a cylinder, there can be flux that like pierces through the surface of the cylinder. That's like having a finite magnetic field. That's fixed, but there's also a flux which goes through the cylinder but never actually pierces any surface, right? So that's like saying, so if I write down what this gauge configuration is for a mu, it looks like this. It's phi, I wrote it as phi sub a over L. So this is the part of the vector potential. I'm saying along the y direction, there's this constant part, phi over L. So if I take gradients of this to calculate the magnetic field, it doesn't contribute to the magnetic field at all. But nevertheless, if you put on this constant A, it changes the boundary conditions that the fermions see. So you can think of it as like a constant twist in the phase of the hoppings.
So this effect, this gamma effect being 1 would disappear in the limit L is infinite. In the 2D limit is invisible.
Yeah, so now you could see it directly in the 2D limit, but you can see it on the cylinder. Yeah. So I'll be a little bit schematic where this -1 comes from. So the idea is if you have some emergent objects coupled to a gauge field, the sort of terms you can write down, which could actually be expressed as physical operators, is to make a pair of objects. Let's say this is at x, and this is at some x prime. This is the object which is charged under a gauge field. So the type of thing that can show up is moving the fermion from point x to x prime. But when you do so, it couples to a Wilson line of the emergent gauge field. So this sort of thing is allowed. This, in principle, has some incredibly complicated relation to the actual spin operators or microscopic electrons. But what you're not really allowed to write down is a term where you create a single, in this case, say, composite fermion. This doesn't have any expression in terms of local operators in the microscopic theory. So it's sort of like you can think about this operator, but it doesn't really exist microscopically. So what that means is, suppose I consider the case where I have two modes piercing, cutting through the cylinder, psi1 and psi2. I can ask what type of operators are actually allowed. You can't destroy a single C1. This is not allowed. You can't destroy a single C2. This is not allowed. But you could make a bilinear like psi1, psi2. This is allowed. And so if you add more and more wires and count how many different types of independent terms there are, this constraint that you can't create something with a net gauge charge removes exactly one mode. And that's why you see the central charge reduced by 1. So in principle, I guess you could use if you had some more complicated situation where there was multiple gauge fields and so on. I don't know of any relevant examples, but you could detect the number of gauge fields from the reduction in the central charge. Yeah.
Does this gauge field have to be U1?
That's a good question. So if you had a Z2 gapless spin liquid, I think you would still see the constraint. It doesn't actually matter whether it's U1 or Z2. Yeah. So I think you'd still see the -1.
But I'm not quite sure I see the connection between the bilinears and the central charge.
Yeah, so the way I know how to actually derive this would be, is to bosonize the problem. So you might be aware that there's this way to write, you can think of a fermion psi sub I as being E to the I phi I, where this phi I is a boson. So if you have multiple components, these are the different types of modes here, you get one boson for each component. And each of them contributes central charge 1. So the constraint, a general operator that you could write down would be I'll write it as psi m vector is equal to E to the I m dot phi I. Well, actually, I should just call this O in general. So this is not necessarily a fermion. It depends on. So m is a vector of integers. And so the constraint is basically that m dotted into 1, 1 needs to be equal to 0. So this is just saying that in net you don't make anything with net gauge charge. So you can think about you started out with a lattice of possible excitations, which has a number of dimensions equal to the number of wires. But then when you enforce this constraint, you reduce the dimension of the lattice by 1, and that's the reduction of the central charge. Yeah, but you can see any bilinear of this form is allowed because it's total gauge neutral. Okay, so now I want to switch to moving on from the gapless case to now can I turn this on actually? Oh, sorry about that. So I want to discuss gap topological orders now and how you could extract them using entanglement measures. I don't have too much time, so I think first I'd actually like to expand a little bit on what Jongbek said about the definition of topological order, because there's actually a couple different meanings to it, and I think it helps to explain exactly what the different types are. So there's two different notions when we talk about topological order. So the one that was discussed earlier was this idea of adiabatic continuity. So it says that suppose you start with a particular state psi, which is a product state, say like all up. And let's say it's the ground state of some Hamiltonian with coupling constant g. We can define an equivalence relation between two different phases, as discussed, which is that we consider a path of Hamiltonians, I'll call it hg of t, that ends at some h of g prime. That has some other ground state psi prime. And we say if a given ground state can be reached by such a path without going through any phase transition, then formally it's as if this ground state basically is just like a product state. So we say any state which can be deformed into a product state by changing the Hamiltonian without going through a phase transition is what's called short-range entangled. And this can be contrasted, which anything which can't be deformed to a product state in this way, we call long-range entangled. So what's a little bit confusing is that this definition, long-range entanglement, is not actually always what people mean by topological order. So a phase with long-range entanglement, for instance, does not necessarily have these fractionalized excitations with Bradian statistics. So an example, for instance, I want to draw a big set of possible phases here. So this particular distinction I'll draw as a dividing long here, LRE versus short-range entangled. So an example of a short-range entangled phase, for instance, is a topological insulator or a band atomic insulator. So I'll say TI, for instance. And two different examples of long-range entangled phases are, say, the Kitaev model. But another example, according to this definition, is the integer quantum Hall effect. So both of these are actually long-range entangled. But the integer quantum Hall effect doesn't have any anyons. It doesn't have ground state degeneracy. So there's another definition of topological order, which is the notion of whether a phase is invertible or not. So we say a phase is invertible or a state is invertible if the following holds. Suppose you want to know whether psi is invertible. The definition of invertible is that there exists some other state phi such that when you stack psi on top of phi, the two of them together are short-range entangled. I'm sure I have two boards to do this. So if I was to draw a picture of this, let me give an example of an invertible phase. Suppose I take the nu equals 1 integer quantum Hall effect. So that's my state psi, and I want to test whether it's invertible. So what I can do is say, well, suppose I'm stack it on top of another integer quantum Hall phase, which is nu equals -1, and call that phi. If you put nu equals 1 integer quantum Hall on top of nu equals -1 integer quantum Hall, the two of them together don't have any Hall conductance and could be deformed in this sense to just a product state. So we say that the integer quantum Hall effect is invertible. And if you can't do this, then you say it's non-invertible. Any questions about that definition? This is kind of, so that's what this line is here. So the phases over here, anything short-range entangled is definitely invertible, because you just don't even need to put this thing, and it can be deformed to a product state. But it's this middle class of things here. By itself, the integer quantum Hall effect can't be deformed to a product state, so it's long-range entangled. But if you are allowed to stack this other phase alongside it, the two of them together can be, so it's invertible. And these are the non-invertible. Like given an actual microscopic thing? Well, I would know how to, so with the Hamiltonian, I would kind of know how to do it. I mean, yeah, doing this constructively, I mean, this definition's hard to work with because it just says there exists some H where you could connect them. It doesn't give you any way to find it. So I'm constructing these relations is difficult. But let me say what some of the properties are. So anything non-invertible is also long-range entangled. This, for instance, is the Kitaev spin liquid, fractional quantum Hall effect. These are what I would call like true topological order, though I think the people's language is a bit ambiguous. So these non-invertible phases are characterized by two things in addition to just this definition. They have these fractionalized excitations, which can carry fractional charge. They have fractional braiding and statistics. And they also have degeneracy if you put them on manifolds like toruses. Then there's this intermediate thing, which is long-range entangled. So like we would have called this topological earlier today. But these don't have any anyons, and they have a unique ground state on any manifold. So those are the long-range entangled but invertible. And then there's the trivial things, which are short-range entangled, which are also always invertible. So unfortunately, I don't think in the field we have a precise definition of which of these we call topological, but these are the actual definitions in play. So, yeah.
In what sense integer quantum Hall is long-range entangled?
Well, so remember the definition of long-range entangled was just that even if you completely forget about symmetry, there's no way to like continuously change your Hamiltonian to deform the ground state into a product state without going through a phase transition. So somehow integer quantum Hall is distinct from a product state, even in the absence of any symmetries. Now, one of the observable consequences is that you have these chiral edge states. And chiral edge states contribute what's called a thermal Hall response, meaning if you have a temperature gradient this way, heat gets transported that way. Because you're just talking about heat transport, that doesn't require any symmetries to talk about besides energy conservation, which you already have just by having a Hamiltonian. Yeah?
So is there a simple argument saying that fractional quantum Hall are non-invertible?
Well, so if we knew that non-invertible implied ground state degeneracy and vice versa, then it would follow. I don't actually know of a simple argument that says ground state degeneracy is equivalent to non-invertible, except at the level of TQFTs. So I want to discuss, well, I guess we're pretty much done, but how numerically you would be able to detect this strong type of intrinsic topological order. What time did we start? I guess we're done.
Started a little late. 5 minutes. Okay, 2:10. That's your absolute. Come on.
Can I lower this now? So at least hopefully I can explain topological entanglement entropy. Yeah, that's fine. Actually, a little bit lower. So on the first day, we discussed the idea of this area law, which is that if you cut out a region B and measure the amount of entanglement between B and A, and ask how does that entanglement grow as you increase the linear size of region A, then the area law says that the dominant part goes as the boundary or perimeter between the two regions. So in 2D, that means that it scales as a first power in the dimension L. So the interesting possibility is, suppose you take the region to be very, very large, could there be a subleading part which is dimensionless and therefore universal? This alpha couldn't be universal because it has units of inverse length, so it's dimensionful, but this is dimensionless, so it could. So this is a beautiful idea due to Kataev, Preskel, and Levin and Wen called topological entanglement entropy. And the idea is follows. We want to show that there can be a constant part in the entanglement which is universal. But you can't just naively take different system sizes and look at the constant part for the following reason. If you're on a lattice and you draw out a region B, you can't make something like a perfect disk. Inevitably, there's going to be regions like corners here. So I'm drawing it as a pentagon. So what we imagine is that the total entanglement has a sum of 3 terms. There's a part which goes as the perimeter, so this is the area law. But then each corner can contribute some completely non-universal amount Ci. And then there's a part we're interested in, which is the universal part. So the question is, how do you cancel out this constant in order to only extract the gamma part? So this is where the ABC construction comes into play. So we imagine that each region A, B, and C has exactly that same decomposition, area plus corner garbage plus the nice part. And then what we do is we can at least as a thought experiment, you can compute the entanglement entropy for each of these regions A, B, and C as well as various combinations of them. So like you could measure the entanglement for A, B together. And then what you do is you form this particular, it's sort of like a connected component of it, which has 7 terms in it. And then you can imagine taking the substituting in that definition there into each of these terms here. And you see various terms are going to cancel. So for instance, this corner here contributes both to SA and SAB. And I had a plus SA here and a minus SAB here. So that part of the garbage actually cancels each other. OK, so you can expand it out, and what you'll find is all the area part cancels, all the garbage corner parts cancel. But because I have 7 terms here, 4 of which have a plus sign and 3 of which have a minus sign, there is a gamma left over. So this particular contribution here is argued to extract the universal part up to something which decays exponentially quickly as you increase the size of everything. So this is the so-called topological entanglement entropy of a phase. And the idea is it's supposed to detect if a phase has this non-invertible type of topological order, which has anions and ground state degeneracy. So I was going to discuss what this tells you about the anions, but I think I'll stop here because we're just about out of time. Thanks.
One question.
If in the wire construction you don't see the peaks in the structure factors, then the theory completely fails.
Well, there could be 2 possibilities. So I chose the density when I calculated the structure factor. And that required that the operator I chose coupled in some way to these bilinears, which transferred a fermion across the Fermi sea. If you're not careful, there could be some selection rule due to symmetry which says that they can't couple to each other. And then it could be due to a selection rule like that. So we actually see an effect like that where you can see that some of the transitions are symmetry forbidden and don't contribute to peaks. But I would be worried if you look at any operator and none of them show peaks, then it probably means that the Fermi surface doesn't actually look like that. Yeah.
All right, so how about we take 4 minutes